Thanks everyone. Today we will be exploring two critical aspects of engineering thought and practice, that is the engineering design process and operational factors in system design. These are not just procedural tools, they represent a mindset and a discipline that lies at the heart of what it means to be an engineer. Whether you are designing a product system or even a social innovation, these concepts guide you in making reliable, responsible, and effective decisions. Okay. So first, let me ask you a question. What do engineers do? Think of this. Okay. So at the surface level, you might say we build things, we code, we fix, we improve. But at the philosophical core, engineers solve problems. Okay. So the engineering design process is the structured approach that enables this. It's not just about making something that works, but making something that works well, meets real needs, and it is optimized with scientific and mathematical reasoning. So this process begins with defining what we are trying to achieve, our objectives, and it doesn't end until we have gone through cycles of prototyping, testing, and improving. So remember, engineering is never about the first answer, that is, it's about refining answers until the best possible solution is reached. Okay. So let's look at the this one more closely. The design process typically follows a sequence of you have 12 steps. Okay. So first is to define the problem. Every design journey starts with clarity. We ask what exactly is the problem we are solving. This involves observation, inquiry, and understanding the real need. And then second is brainstorm possible solutions. So at this stage, we encourage divergent thinking. All ideas are welcomed without judgment. So innovation thrives when we don't censor ourselves too early. And then third is the research ideas or explore possibilities. Engineers are not artists creating from a void. We stand on the shoulders of prior knowledge. What solutions already exist? What technologies are available? What are the trends? Then fourth is established criteria and constraints. We need to be realistic. What must the solution achieve? And what limitations are we working under? Budget, time, materials, or regulations. And then fifth is to consider alternative solutions. We don't settle for the first idea. We weigh multiple options, compare strengths and weakness, and begin to see which paths might be more promising. And then select an approach with logic and clarity. We choose the solution path that best fits our criteria and constraints. So this is not the guesswork, it's thoughtful selection based on evidence and reasoning. And then seventh is develop a design proposal. A proposal is where we put our chosen approach into a structured plan. It outlines what will be done, how, and with what resources. So this is a blueprint for execution. And then eighth is make a model or prototype. So we bring the idea to life, even if just as a mock-up. This prototype can be physical or digital, low fidelity or high fidelity. So the goal is to test, learn, and visualize. Then test and evaluate. This is where philosophy meets data. We ask, did it work? Why or why not? What can we measure? Feedback from this stage is invaluable. Okay, then refine the design. 10th step is. So based on the test results, we make improvements. This can be iterative, multiple rounds of testing and refining until we are satisfied with performance. And then 11th is create the solution. So now we implement the final design in its complete form. This is not just about building, it's about building with excellence and responsibility. And then last, communicate the results. So finally, we document everything, what we did, how we did, and why it matters. So this includes technical drawings, reports, presentations. So this stage ensures knowledge is shared and decisions are transparent. And then when we speak of system design, especially in fields like mechatronics, computer science, or large scale engineering, they are more at play than the mechanics of the system. So operational factors determine how well that system works in the real world. System design must ensure efficiency, reliability, scalability, security, user satisfaction. It is not about how something is built, but how well it performs under real world conditions. Okay, so let's break this into different factors. So integrity and consistency. In engineering systems, particularly those that store or transfer data, consistency is the key. Imagine a banking system where your balance updates on one server but not another. Then it is a chaos. Integrity means maintaining accuracy and trustworthiness of information throughout the system. Consistency ensures that no matter where or how the system is accessed, the experience and data remain uniform and reliable. Systems must be fault tolerant, meaning even if something goes wrong, the design prevents disaster. This requires redundancy, backups, and smart architecture. And then performance and scalability. A well designed system performs efficiently, but more importantly, it can scale. It can grow with demand. If your design is perfect for 100 users but it fails 1000, it is not truly robust, right? Engineers must anticipate future needs and build elastic architectures, ones that can expand without breaking. So think about how cloud platforms which allow applications to scale automatically. That's engineering foresight in action. And the next is deployment strategy. It is not an afterthought, it is a strategy. Okay, so today we use a CI or CD pipelines, continuous integration and continuous deployment to automate builds, tests, and releases. Whether the system runs on the cloud or on premises, the deployment process must be repeatable, testable, and efficient. A good deployment strategy reduces downtime, prevents human error, and allows quick updates. So, this is essential in modern engineering practice. And then next is security. As engineers, we are guardians of both physical safety and digital safety. Security must be built into the design, not added later. Okay, from encryption to user authentication, from hardware locks to software firewalls, every layer of your system must anticipate and defend against potential threats. So security is not paranoia; it is a professionalism. Okay. And then user experience and inclusivity. So what good is a powerful system if no one can use it? So it is a soul of user experience, which is the soul of modern engineering systems. Systems must be intuitive, accessible, and inclusive. Inclusivity, which is meaning designing for all users, including those with disabilities, language barriers, or technological limitations. It's not just a good design; it's ethical design. When engineers think about the end user, the system becomes not just functional but human. So next is recovery and planning. So even the best systems can fail, but great engineers plan for failure. Disaster recovery and business continuity ensure that in case of outages, data loss, or cyber attacks, the system can bounce back with minimal impact. This involves backups, alternative workflows, and well tested recovery protocols. A robust system doesn't just work when things go right, it keeps working when things go wrong. Okay, and next is unit testing and application performance monitoring. That is, finally, let's close with two important practices, that is unit testing and application performance monitoring, that is APM. Unit testing means testing each part of the system individually to catch errors early. It builds confidence in your code. And then APMs, that is application performance monitoring, are the tools that monitor how your system performs in real time, tracking the metrics like load time, crash reports, server health. Okay, so these practices which allow engineers to maintain, improve, and evolve systems over time. They transform design from a one-time event into an ongoing responsibility. Okay, so design is both art and science. The engineering design process gives a structure. Operational thinking ensures that structure thrives in the real world. Okay, thank you.